Hello, this is Matteo talking about federated online adaptation for deep stereo. Stereo matching is the task of estimating depth out of two rectified images. For each pixel in the left image, we look for the corresponding one in the other. This allows for finding out the horizontal shift between the two, also known as disparity. This information allows for obtaining depth by means of triangulation. The very first deep networks designed for this task suffered of severe domain shift issues, for instance when transferred from synthetic to real images. Before 2020, domain adaptation was a solution for softening this problem. This could be done even at test time, yet introducing unnoticeable overhead. On the contrary, state-of-the-art solutions nowadays have outstanding generalization capabilities, as we can notice from these examples. Despite this remarkable achievement, they are still far from running in real time, in particular when deployed on low-power devices. Furthermore, generalization remains an open challenge, in particular when the domain shift becomes harsher. In this case, even the accuracy of state-of-the-art solutions still drops. Thus we wonder, can we have a fast network capable of adapting in real time even on those domains where state-of-the-art networks struggle? Furthermore, when our hardware cannot support adaptation, can we still benefit from it in some way? In this paper, we answer to the first question by introducing a modern compact architecture capable of running in real time even on low-power devices. And to the second by introducing the first ever federated adaptation framework for deep stereo, in which a single client not capable of adapting can demand the adaptation process to the cloud. For this purpose, we revise our previous work and introduce MadNet2, a new baseline for online adaptation for deep stereo. Specifically, we replace the fixed range correlation layer with the all pairs correlation module from RAF Stereo, and train it with much stronger data augmentation derived from the latest advances in the field. Then, we introduce our novel framework for online adaptation. Let's start by considering a single stereo network running in an unknown domain. To counter the domain shift, the network itself updates its weights by computing a self-supervised loss on each incoming stereo pair. This process is very expensive, yet we can reduce the overhead by only updating a portion of the wall weights. This makes the stereo network getting better and better over time. Given this background, we now introduce our federated adaptation framework by deploying a remote server. During its whole life cycle, the server will remain listening to the cloud, waiting for communications from clients. The single stereo network adapting on its own domain is itself a client, sending at regular time intervals its updated weights to the server. The server can receive updates from multiple clients, each one running on different domains. These updates are aggregated and sent to listening clients, that are those not capable of adapting on their own, for instance because of their limited hardware resources. Accordingly, when this latter receives the updated weights, it will benefit for free from the adaptation carried out by the other clients. However, this framework introduces a communication overhead, which can be reduced by only exchanging a portion of the wall weights updated by the clients. We now show some results on Kitty. Despite MadNet2 initial accuracy is much lower compared to state-of-the-art architectures, it can easily catch up by means of single domain adaptation, with federated adaptation yielding equivalent results and sometimes even better. We also run experiments with other real-time architectures, confirming that they can benefit from both single domain adaptation as well as from federated adaptation. Here, we plot how the accuracy and the amount of transfer data depends on the update frequency and the amount of adapting clients. By transferring only portions of the wall weights, we can trade accuracy for the amount of data being transferred. We conclude with some results on driving stereo, for better appreciating the benefits introduced by both single domain and federated adaptation. Thanks for watching.